I'm Professor Ron Smith from the Department of Geology and Geophysics, and if you're in the right place, you know that this is the course called The Atmosphere, the Ocean, and Environmental Change. There's a lot to talk about today. Some of you are shopping. I want to be sure you get enough information about the course to make your decision about whether to take it or not. And for those that are definitely in it, I want to get you started towards some of the course material that we have in this course as well. So as I will usually do in the mornings, I'll have some notes in the upper left there, and I want to run through some of those. This is just informational stuff, logistical information about the course. There was some confusion about this. The lab is required. So everybody that takes this course takes the lab, and everybody that takes the lab takes this course. You get graded separately for the two, but the two are really, the subject material is merged and coordinated.
Cool. Like I finally got this all working. I'm gonna drop the audio on the music. 3%. Make that 5%. 5%. It's good. We're gonna play a new game, and I think we're just gonna use the default map, default everything. I just got this game, so I haven't had a chance to play it at all. However, I have watched a metric fuck ton of people play this game, so that should be all good. And then I found a like what is this exactly? It is Atmosphere, Ocean, and Environmental Change with Ron Smith from Yale Courses. It is a 36-part lecture series. We may or may not sit through all of them at some point. Who knows? But anyway, we will see how this goes. I am just coming off the back end of a cold, so if you guys hear me blow my nose or cough or sneeze, I apologize, but it's going to be happening. And to get the show started, I'm going to blow my nose right off the bat. Now, I could play a game like Anno 2070, which is all about dealing with the aftermath of climate change, but I don't want to play that because I got this game and it's new and I like how it looks and I want to play it. So we're going to be playing that. As far as this lecture series goes, I'm just going to be watching it to try and get more of a... Like, I feel I probably already have a pretty good grounded baseline for, like, climate stuff, but I want to check myself. And so I want to, like, kind of go over the groundworks here, at least at a collegiate level, and kind of make sure that I know what I'm talking about, what I'm talking about. So yeah, let's go ahead and dig in. I have the... As you guys probably noticed, I can probably... as you guys... Fuck me running. As you guys noticed, I can only really have the stream up when I'm looking. Like, it's... I'm using both screen captures right now, so my screens are all full up. Which means at the moment, what I'm doing is just keeping a track on chat through my phone. I'm going to work on that in the next couple of days. Hopefully we'll see. And if the stream picks up and I'm able to actually stream on a consistent schedule, maybe start making some moolah off of this, and I can actually start expanding. I could get a third monitor, because these monitors are dog shit. So let's go ahead and get ready.
In a certain way, so you have to take both of those. That means when you're signing up for the course, be sure to sign up for the lab as well. It has a different course number. For example, EVST 201 is this course, 202 is the lab. Or if you've signed up under geology, it's 140 and 141 is the lab. Now,
let's see, what do we have?
We also the classes
blast
server.
Furnace, and
they're separate sites, so I'll be sure to register on both of those because I'll be posting information about the lab on the lab course number. Now, the labs aren't going to start actually till week 3, so we're not going to do lab section signups yet. But I will tell you that the labs are on Monday and Tuesday afternoons. There's 4 sections altogether, and you've got to be able to fit into at least one of those, and we hope more than one because we're going to have to even you out. But those labs are at 1:30 and then at 3:30 on both of those days. So we'll be doing those lab signups next week when you have a better idea of what your schedule is like. But try to keep those Monday and Tuesday afternoons open so you can fit into one of the labs, because if you can't take the lab, you can't take the course. Let's see, there's already a problem set posted on the classes server, and it is due next Friday, a week from Friday. And you may ask, how could I have already posted a problem set when I haven't given a single lecture about the course? Well, that's because this particular this particular problem set is kind of a warm-up. It's got questions on there that you can do with an elementary knowledge of high school physics, and I'd like to get you started on that, both because we need you to be fresh and familiar with those subjects, but also those of you that don't have a good background might want to use that as a guide as to whether this is the right course for you. So take a look at that problem set as soon as you can, and if you have any problems with it, talk to me, talk to your TAs. Speaking of TAs, let me see if I can introduce them to you. Ravi is there. Jennifer is there. Is Meng here? Meng is right there beside them. And Srikanth. No Srikanth today. Okay. And by the way, Melanie here on the left, my right, is going to be helping with the taping transcripts. So we're going to have this course taped. And I'm afraid these tapes are not going to be available to you during the semester. There's too much of a lag time, I think, to get those to you. But I don't think it'll be a problem in class. One thing I want to mention, though, this course, well, it seems like we got a pretty big class here, but still, even with this class, it's a very convenient room and a very convenient class to have a lot of discussion, questions, answers, and so be prepared for that. Don't be shy about asking questions, and I think that'll really add a lot to the course if you get in the habit. If you've gone for a period or two and haven't asked a question in class, you should ask yourself why, because it's probably not the clarity of my lectures. It's probably that you're just reluctant to put your hand up. So try to gauge this a little bit. And if you're asking too many questions, which hasn't happened yet, but if it happens, I'll tell you about that, and we can scale it back. The textbook is in. I went down to the bookstore yesterday and I saw it there. Didn't look like they had that many copies, but I should mention that
groundwater there,
if you get
sand, iron, more
copy
water,
that's an edition or two old, that would be okay, and you might be able to really save some money.
Probably got to put a big smelting
but
thing
get that book
here.
right away, because you're going to need that starting immediately. And if
farms
you have to order
down
online,
here.
it's going to take a couple of weeks. That's probably not good. So get that coming to you.
our
But anyway, the book is this one, Essentials of Meteorology, and a word or two about it. Yeah, well, it's a descriptive book primarily. It describes things that go on in the atmosphere and the ocean.
We got a long time before we get to that.
And that'll be really great. That'll supplement what I do in lectures. The course, however, is more quantitative than this.
Yeah. Okay, course overview. Don't care about the course overview.
So
here we go. Weather.
there's time on this axis and feet above mean low water. So this is the record of tides for New Haven Harbor. It's at the Coast Guard station, right?
Oh man, this is gonna suck for part of this. So I don't know if these links that you're seeing here on screen will work anymore. Not that you guys care, because NOAA doesn't exist anymore. It's now the NWS, or it's no longer National Oceanic and Atmospheric Administration. It is now the National Weather Service, which is a much less cool name, but whatever.
On the east side of the harbor there. And the blue curve is what was predicted for the tides based on the moon and the sun, right? The moon and the sun their gravitational pull produces a tide in the ocean. Here in New Haven and most places around the world, it's a semi-diurnal tide. That is to say, it's a twice-a-day tide, 2 high tides and 2 low tides, and that's what you see in the blue curve. The red curve is what's actually measured. They've got a water level gauge there, and as it goes up, they record that. And now this date goes back to the 28th and the 27th, which was last weekend. And what you see here is that the seawater level rose quite a bit above what was predicted from the normal tides. And of course, that's what's called the storm surge, right? So as Hurricane Irene came up the coast, and with the winds blowing counterclockwise around it, as it approached, the winds were from the east. In fact, that's on this curve. I'll show it to you in just a minute. Well, that wind from the east pushed water into Long Island, and the water level rose. And they've subtracted one curve from the other to get the green curve. So that's the difference between the observed water level and the predicted tide level. And you see that it rose about 4 feet above normal and then dropped a couple of feet below and then came back to normal. So that's a typical example of what happens with sea level as the hurricane comes up. Now, here's the wind data. It's too small for you to read from the back, so I'll try to walk through it. The same time scale is on the bottom here. It's spanning about 3 or 4 days. This is in knots, which is a traditional unit of wind speed.
Oh, that
Unfortunately,
ye
it's not
olde.
the one we'll use primarily. We'll use meters per second, but knots is a traditional speed. A knot is a nautical mile per hour. So it's kind of like a mile per hour, but a little bit greater. So the wind speed increased as the Hurricane Irene approached, and from the little vectors
this is
you can see the
cool.
wind was from the east.
Oh, we get to
It reached a peak of about
Look
40,
at
42
this.
knots, and then as the storm moved away,
to like
the wind speed decreased.
fucking
But then
make
the
our
wind
people
was from
happy
the
with
west.
protein and shit.
Remember, so just to sketch
Guess
this
that's
out,
probably
if I can for a second.
tofu, bread, corn, potatoes,
So here we are in New
meats,
Haven.
eggs,
The cyclone is
tofu,
like this.
sausages,
Winds going around in that
vegetables, fruits,
As it approaches us, the winds are going to be
cake
from the
and
east,
chips, probably.
and then as it passes by,
I mean, I don't know about you,
a
but
day
that's like
later, it's up here. The winds have the same direction around it.
get rid of
Suddenly
the
winds are from
beef and the
west.
sausages.
So you're seeing that
Hell yeah.
pattern there, and then of course that's
diet
what's
right there.
reflected in the storm surge. First, it pushes water into Long Island Sound, then it pushes the water back out of Long Island Sound. So it's not too
Go
complicated,
ahead and
and the
speed this
data
up
is
a little
right
bit,
there
shall we?
for you to see.
6 people available for work. We could do a bit of research.
So here's
lab,
another
I
one.
guess.
If you go on to water data USGS, that's the United States Geological
There we go.
Survey,
Assembly Electric.
and
Or Assembly
hit
Manual,
on
pardon me.
the Quinnipiac River, which is the main river that comes down through New Haven. There's 3 rivers. We're going to do a field trip along the Quinnipiac as part of Lab 2 or 3, so you'll learn a lot about the Quinnipiac. But I went on just after the hurricane to get this data. This is the river discharge. Again, it's not in a metric unit, I'm afraid. It's in cubic feet per second. That's how much water is coming down the river. And these are dates along here, August 23rd, 4th, 5th, 6th, so on. So
Mechanical
that, of course, is the big rise. This is, by the way, this is a logarithmic scale. So that's a
do
really
2
big
more of
increase
these, I guess.
in the amount of water coming down the rivers. And then, of course, that's because of the heavy rain that fell from the hurricane.
It's like 3
So
in between
check
each.
that one out as well. Let me see what else I have that I think is really important. Well, the radar, I love to watch the radar. You can get there
Radar
a
is
lot
always
of
fun.
different ways. For example, radar.weather.gov. But usually I go right to the closest weather radar to us is on Long Island. It's about here at a station called Upton, UPTON. So if you just Google Upton radar or Upton NOAA radar, you'll go right to that site and you get a nice visual representation of the precipitation in the region.
Hey, we
One
got a
thing
new
to remember about
population.
radar, I think you know
Yay.
what it is. It's a microwave signal that gets sent out from the radar antenna.
Basic
scatters
farming, farm
off
and potatoes.
raindrops, and then comes back to the receiver. And from the time it takes for the signal to go out and back, you get the distance. And of course, from how the antenna was aimed, you know the azimuth angle, so you can figure out where that is. And it's put together in a nice map like this. This was taken just as as the front part of the cyclone was coming into southern New England. And you see this nice heavy rain shield out here. The eye of the storm is probably about here. There wasn't a very well developed eye, but the center of it was probably about here. And the back.
Okay, so in case anyone's wondering, this is a radar picture of a hurricane that's hitting hitting landfall. I think that's New Jersey right there. What you're seeing here by the radar is the blue is like less dense cloud cover, so less water vapor, so a lower return signal, whereas the green is a much higher return signal for water vapor. Which is how you get these differences in the picture here, and you get this via Doppler shifts. So that's really cool, and that's also why you get this weird shadow line right here, is because there's something blocking line of sight right there that expands outwards, and that's probably like, I don't know, I had to make a guess, like a cable or something. Like it's just this piece of thin metal that the Doppler can't see through. So it fucking makes like a citywide hole on the edge of the range there.
Backside was fairly dry, surprisingly dry. We'll talk about that later on. Some people think that it was transitioning away from a tropical cyclone to a different type of a storm at this point, but that's getting ahead of the story. But you can check, I check it frequently when I'm about to walk out to go someplace on campus, and sometimes I'll go onto the Upton radar and just check the radar to see if it's raining. I've got a window, but what I really want to know is not whether it's raining now, but is it going to rain in 5, 10, or 20 minutes? Well, if I see a big squall line coming towards New Haven, then I can decide whether maybe I can sprint to where I'm going before it gets there, or maybe I better just wait until it runs through, and then I'll walk out to my car or walk out to my meeting. So that is a very nice, in meteorology, we've got a funny word for that. We call it nowcasting. It's like forecasting, except it's forecasting for just the next few minutes. And the best way to do that is with the Upton radar, because that'll tell you, New Haven's right there, and it'll tell you if there's a little thunderstorm or something just about to move over New Haven. So it's very, very convenient for that purpose.
All right, so
Another
now
great
is
one,
when
of
we're going to
course,
start
is
getting
the,
into
satellites.
utilizing this shit up here.
And here's a picture of Irene.
Let's go
Now,
ahead
there's lots of ways to
and
get at the satellite data.
that'll be for iron, coal.
www.goes.noaa.gov is one way to do it. And GOES stands for Geostationary Environmental Satellite. This means it's a satellite that is it's over the equator, and it takes 24 hours to go around its orbit, just like the Earth takes 24 hours to spin on its axis. So it stays over the same point on the equator. So we say it's geostationary. It's like it's parked right up there, and it's the best satellite for watching cloud patterns develop and move, because you're not just getting an occasional snapshot when the satellite comes back around. No, that satellite is there and is taking a picture about every 10 minutes. So you get a really good way to follow the structure of these cloud patterns as they're swirling around. So there's a good example. Now, also notice these clouds are quite different than the ones up here. The radar showed that these were not precipitating, but these were. So the deeper clouds with the big anvils on them were precipitating, but these low-level clouds were not at that moment. Any questions on this? Okay, well, do I have anything else? Oh yeah, so this gets a little more techy maybe, but I love it, and that's getting the balloon sounding. So the National Weather Service launches balloon.
Hey, now. I don't need any of that. Get your mind out of the gutter. It's not that type of sounding.
Weather balloons twice a day from a couple of hundred places around the United States, and 400 or 500 around the globe. And they're all accessible. The balloons are launched at 0 and 12 universal time. You're going to have to become familiar with what we call universal time. Sometimes we call it Greenwich Mean Time. In the military, it's called Zulu time. We'll most of the time call it just universal time. And so 0 and 12 universal time, when we're on Eastern Daylight Time, like we are right now, would be 8 o'clock in the morning and 8 o'clock in the evening. So those balloons are launched at 8 o'clock in the morning, 8 o'clock in the evening. And they take about, they'll launch them a few minutes before that time, because they take a couple hours to rise. But if you go on to, what I usually do is go on to the University of Wyoming website, because they've got a really great website where you can get all the soundings all the way back in time. Back 50 years, you can get soundings from all these different sites. So that's a really handy one to go into. So what I did here was pull off the, I forgot to say, the closest radiosonde site to us is also Upton, New York. Same place where that radar is. They launch balloons from there as well. So what I did here was to go on to the Upton, Wyoming site, pull down the sounding for as the storm was approaching, and then as it was leaving. So this is a balloon. This is a balloon carrying a small instrument package. You'll be working with this kind of data later in the course. So this is a little bit of a preview. But what's plotted here is, well, I'll say altitude, but really it's pressure, because that's how we know how high. That's how we know how high the balloon is, from the pressure that it's recording. Pressure decreases as you go up in the atmosphere, so it's a convenient way to keep track of your altitude. And then on this scale is temperature, and two lines are plotted. One's the air temperature, one is the dew point. So when they're close together, that means the air is saturated with water. So that's not a surprise that as this hurricane was coming over us, the air was saturated at least 3 or 4 miles up in the atmosphere. Maybe that's not saturated, but it probably is too. Probably that's just an instrument error or something to do with ice versus water. It's probably saturated all the way up. And then the winds are given over here in a...
Let's move on to retaining an atmosphere, shall we?
Talking last time about, well, we asked questions like, how do we know there's an atmosphere? I wanted to follow that up a little bit more. Someone had mentioned atmospheric pressure as being something that's really important for knowing there's an atmosphere. And I said, well, we don't really sense it very well because our bodies tend to equilibrate inside and outside. When we go up in an elevator, we're moving into lower pressure, but we may feel it in the ears, but we don't feel it most other places on our bodies. But then I was thinking there are some other ways that we could sense pressure. And I had these suction cups in my office. They're not sticky in any way, but when you push them together and remove the air that's inside, then you only have the atmospheric pressure acting on the outside and nothing on the inside. So when you try to pull them apart, try that. Watch out for your elbows there. Everybody gets to try that today. So you'll see that's atmospheric pressure, right? Again, watch the elbows so you don't get the guy next to you. Now, you were walking
PSI.
up to class today, and you remember that we got one of the pieces of advice that I gave you for this course is to develop a habit of looking up in the sky. And what did you see this morning when you walked to class? Blue sky. Now, what if there had been no atmosphere? What would you see when you looked up? Black. Right. So that blue sky is light that's been scattered to your eye by the molecules in the atmosphere. So that's a good way to know there's an atmosphere. Another one on the pressure. When you're having lunch, if you're drinking from a straw, I don't know if you do that, but when you're drinking from a straw, you may think you're sucking that fluid into your mouth. Actually, you're not. You're dropping the pressure a little bit,
and allowing the atmosphere to shove it into your face.
Pushing down on the top of the fluid, that's actually what's pushing it up the straw. So you're not doing much. The atmosphere is doing most of that with its atmospheric pressure. So we'll continue to think about these day-to-day ways in which we will know that there's an atmosphere. Are there any questions on these issues before we begin? Any things we spoke about last time? Nothing? Okay. Well then, I want to move on to a subject today which is related to what we had last time. And that is which planets have atmospheres?
In our solar system, I think the only one that doesn't have an atmosphere is Mercury.
And why?
Right?
And it turns out
Venus has an atmosphere, Earth has an atmosphere, Mars has an atmosphere, Jupiter, Saturn, Uranus, and Neptune all have an atmosphere.
At the top of the atmosphere can escape the planet's gravitational field. Now, let me be clear on this. The molecules in this room are traveling a very short distance, and then they encounter another molecule and they collide, and then another short distance and they collide. So there's no chance that these molecules in the lower part of the atmosphere could ever escape, at least not immediately, because they're surrounded by other molecules. But the molecules at the top of the atmosphere, if they're heading upwards, and some of them are, they might just leave. They may just get fed up and decide to leave the Earth's atmosphere. So we have to come up with some way of understanding that process and to find out when it works and when it doesn't work. So to do that, we need to define something called the escape velocity. It's defined as the velocity needed to escape from the gravitational field of a planet.
Yep.
Now, if this was a
So the reason I have
course
this
in
all
physics,
paused is
we
because I
would
want
derive it. It's not a
I want
difficult
belts before I do anything.
derivation, as it turns out, but I'm just going to give you the formula for it. V escape is given by the square root of twice times little g
This
times
is going
big
to
R.
have
Little g is the
construction
surface gravity of
parts.
the planet.
This is going to have electronics. This is going to have mechanical
For
parts.
Earth, by the way, I think you know what that number is. G is 9.81
meters per second squared.
It's given in units of acceleration. In fact, it's just the rate, if you drop something, it's the rate at which it accelerates towards the surface of the Earth. And big R in this formula is the radius of the planet. Now, to be consistent, oh, by the way, for Earth, this is about 6371.
Fluid storage.
Earth
Now that's
is not
nice.
exactly spherical, so this number is a little different depending where you are.
This is true.
It's
We live
about
in an oblate
6,400
sphere right now.
kilometers, the radius of the Earth. So let's work out an example of this and then see what it means. So for Earth, then, V escape, let's compute it for Earth. It's going to be the square root of 2 times 9.81 times the radius of the Earth. We have to work in consistent SI units, international system, or so-called metric units. So I need to convert that to meters. So that's going to be 6370, and then 3 more zeros to get it into meters. And you know how to do a square root on your calculator. That comes out to be 11,180 meters per second. That's the escape velocity for planet Earth. Now, it's going to be different for other planets because they're going to have different surface gravities and different radii. But that's the escape velocity for planet Earth. So what does that mean? If I'm at the top of the atmosphere, there's the Earth, there's the atmosphere, and if I've got a molecule at the top that happens to be heading upwards, if it has a velocity less than this number, it's going to go up for a while and then stop, and then gravity's going to bring it back to the back into the atmosphere. If I have a molecule that's moving faster than that speed, it's going to leave.
I feel like I should be playing Kerbal for this part.
Again in the vicinity of planet Earth.
Well, that's not entirely accurate.
So this here is when the upward velocity is greater than V escape, and this is when V is less than V escape. Something interesting about this formula, notice that the mass of the object that we're talking about does not enter into that formula.
Why would it?
So this would apply for a molecule or for a rocket ship. When they launch a rocket into orbit or to another planet, it's exactly that same speed that they have to accelerate the rocket to in order to get it to escape from our planet's gravitational field. So this is kind of a universal number for the planet, independent of what the object is. Any questions on that? So that's pretty helpful, but it's only half the story because we have to know something about what the molecules will be doing. So the typical speed of a molecule I'm going to call it V sub MOL, is given by the square root of 3 R bar T over capital M. Now, this is a formula you might derive in a chemistry class, and maybe you've seen this one before as well. In this formula, R hat is the universal gas constant. T is the temperature.
That was universal gas constant.
Of the gas. It must be expressed in kelvins to work in that formula. That is in absolute units. And what?
Okay, so the universal gas constant is the molar constant is denoted by R. It's the constant of proportionality that relates the energy scale in physics to the temperature scale and the scale used for the amount of the substance. Thus, the value of the gas constant ultimately derives from historical decisions and accidents in the setting of units of energy. Okay, so it's one of those things that humans made up that we just live with. Okay, gotcha. Continue.
What else do we have there? M. M is the molecular weight of the molecule in question. Now, I think you know how to go back and forth between temperature units, but let me just remind you, if you've got a temperature in degrees Celsius, you have to add to that approximately 273.1. Sorry, that's an add. Temperature in Celsius plus 273.1 will give you the temperature in kelvins. Kelvins
Seriously,
is on the
just a
absolute
giant
scale.
goddamn limestone mountain.
Before we go any further, let me just give you a little table of these
Cool.
molecular weights for a few of the gases that we might be interested in. I'll make a table here for a single hydrogen atom by itself. It has just one proton in its nucleus and no neutrons, so its molecular weight is 1. This will be the column of molecular weights down here. Hydrogen usually occurs in the diatomic form, two atoms fastened together with a bond, and of course the molecular weight for that would be 2. Helium has 2 protons and 2 neutrons in its nucleus, so it has a molecular weight of 4. Nitrogen, and most of the gas in this room is nitrogen. It appears in the diatomic form, two nitrogen atoms together. Each one has a mass of 14, so the molecular weight of the N2 molecule is 28. Oxygen, which composes most of the rest of the gas in this room, again occurs in the diatomic form. Each one is 16, and so that's going to be 32. And carbon dioxide, which you're breathing out, carbon is 12. If I add that to 2 O's, I'm going to get 44 for the molecular weight of carbon dioxide. So you've probably seen those numbers before, but that's what I'm talking about when I refer to the molecular weight here. Any questions there?
What is the R expressed as? Like, because there are like different numerical values. Like,
The units of it? The question is about the units on universal gas constant, and I usually give them this way. I usually write them as units on that would be joules per kilomole per degree Kelvin. By the way, either at the end of this period or the beginning of next, I'm going to spend about 15 minutes talking about units. And so if you're a little bit rusty on units, stand by. We're just about to give a review of the units, especially in the SI system, which we'll be using in this course. Thanks for that question. So let's do an example then for, let's say that the temperature.
Storage.
Here's my example.
So up here, we're also going to need some loose storages.
Let's say I've got a gas that's at a temperature of 15 degrees.
Now we're going to need storage
so
for not only iron ore, but also coal.
If it has a molecular weight of 2, that would be
Want to go ahead and give us some
hydrogen
space
gas.
here. So I think
We can put those numbers into the formula. It's going to be 3 times. Oh, I didn't give you the value, did I? The value for our head's about 8,314.
Be good for coal.
Plus some other decimal places after that. But so let me work it out in this case.
Something here. I'm going to go ahead and pause these two because again, I need to have the things.
Square root of
another loose storage we're going to need is an output for the slag.
Temperature is going to be 288. We're going to divide by 2. And for that, I get 1,894 meters per second. And let's do it immediately for nitrogen, because that's the one that's relevant to this room. So for a molecular weight of 28, well, the formula is going to be almost the same thing, isn't it? It's going to be 3 times.
So we're kind of getting our layout here.
8,314.
You're starting to see how it's going to come together.
288, but in this case, divided by 28 inside the square root, and that comes out to be 506 meters per second. So that's what typically the molecules in this room are doing. That's pretty fast. I mean, that's something like 1,000 miles an hour. Those little molecules are really moving fast in a temperature, in a gas of the temperature that we have in this room. So now we've got the two sides of this argument started.
Now,
it's
something else we have here. So you can see here, this is oil. So we do need to start getting an idea of like some level of distillation going, right? We can see here that this distillation is going to require crude oil and coal, and will produce diesel, wastewater, and exhaust.
Consider for a moment what would happen if V escape was approximately equal to V molecular. In other words, if those two numbers were about the same value in an atmosphere, what would happen? Well, at the top of the atmosphere,
and we're going to want to dump.
Some of the molecules are moving down, and some of them are moving up. Now, I have to say, this is a typical molecular speed, but some of them are moving slower and some of them are moving faster. There's a complete distribution of speeds. So it's not every molecule that would be aiming up and have a speed equal to or greater than the escape velocity. Probably only a quarter or a fifth.
That's something we do have
of the molecules up there would happen to be aiming up with a speed that would be fast enough to leave. But remember, they would leave in an instant. In a fraction of a second, they would be gone. In another fraction of a second, the molecules remaining would have had more collisions, and now some of them would be aiming up with a speed faster than the escape velocity, and they would leave. And this would continue. So in fact, if this were the case, if the average molecular speed was about the same as the escape velocity, we would have an explosive loss of the atmosphere. It would be gone within moments. So when we're asking about whether a planet can retain an atmosphere, we have to use a more restrictive criteria than this, because remember, the Earth has been around for something like 6 billion years. So we have to use a conservative estimate. The one that I like to use is to say the escape velocity, if that is greater than about 10 times the molecular speed, then an atmosphere can be retained. it's kind of a rule of thumb
Look at all of that.
to put that factor of 10 in there, to take into account the fact that some molecules are moving faster than the typical molecular speed, and we have to retain it not just for an instant, we have to retain it over
All this shit
millions
too?
and
Oh
millions of
boy.
years. So let's take a look at Earth for a second and see what we can conclude from that. If I multiply this by 10, I get 18940 meters per second, about 19,000 meters per second. That is actually greater than this. And so we conclude from that that hydrogen could not be retained on Earth, could not be retained on Earth.
Tends to float away, yeah.
You follow that logic? Any questions on that? Let's do the same thing for nitrogen. If I multiply this number by 10, 5060, that's about 5,000 meters per second. That's only half of this number. So we conclude that nitrogen could be retained. Well, as it turns out, there's very little hydrogen in our atmosphere. And that's probably why, because any hydrogen that was there in the beginning has been lost by this process. Instead, our atmosphere is dominated by nitrogen, mostly, but also oxygen that would move even a little bit slower because it has a molecular weight even greater. So that could be retained. There's some carbon dioxide in our atmosphere. That could be retained. So we've already learned something about the Earth with this little exercise. It's probably lost its light gases like hydrogen and helium, even if it was there in the beginning, which I think it probably was. But it's been able to retain the somewhat heavier gases, such as nitrogen, oxygen,
So many away.
and
so far.
carbon dioxide.
Okay, so what do we want to do now?
Questions on that? Yes.
Let's get a maintenance depot going, shall we?
Well, you'd have to go beyond. This is kind of a crude argument. It doesn't
This
tell
will
you the
keep
rate.
our
You'd have to
trucks
know,
and
to do
stuff
that,
working.
you'd have to know something about the rate at which molecules are colliding and restoring that set of molecules that are aiming upwards. It would depend on that to a certain extent. And there are some other processes that may play a role. For example, the solar wind coming from the sun will sometimes take the light molecules and sweep them away. I've not included that in this argument. So there's a few other things you'd have to include to get a quantitative estimate of that. This I have to admit then, that's a good question, and this I would say is more of a qualitative or an approximate approach to that question. It doesn't include all the physics, and it doesn't give us a quantitative answer of how rapidly the atmosphere would be lost. So, but that's what we can do with what we have here. Other questions? Yes.
It's not
Well, it's a fudge factor. I admit this. The question is, this factor of 10, where did it come from? What I've done is try to use a number that is consistent with some of these more sophisticated calculations. You can find in the literature people have worked out this problem in great detail because it's of central importance to the history of the Earth. And from those complicated calculations, I've extracted this as kind of a rule of thumb. So I don't know that I would rely on this, but it gives us a rough estimate of how to judge things. I'm going to show you in a minute that this argument makes some sense when you look at all the planets together as well. And that won't necessarily confirm that that factor 10 is right, but at least it'll give us a sense that the argument is approximately correct. Okay, now, so what I did following
we're going
this
to be good on
kind of
that. Let's go ahead and get some
was to
concrete.
take all the
production
planets
going,
and
right?
moons in the solar system, and I did an estimate for the temperature of each one.
So we're going to need a concrete mixer.
And-
And this is going to need 2 cement, 1 crushed slag and 2 water to make concrete slabs. Well, how do you get crushed slag and water? Well, luckily we know we have a rainwater harvester, so we can get that pretty easily. And then I think probably you just use crusher, right? And crushers take rock and turn it into gravel, or they take slag and turn it into crushed slag. That's equal amounts for both, so it's pretty easy that way. And then, of course, a rotary kiln will take limestone and coal and turn that into cement and exhaust, as you're cooking the limestone and turning it into cement then. So what we'll need to do long term, anyways, is set up some area, maybe over here. So let's say right here. This is a nice little area. Go ahead and put a guy up there. Pause this for right now, but this would be for wood. I want to clear a bunch of wood up here anyway. Distillation. Yeah, it's all a big fucking thing. Yes, I know it couldn't store all the potatoes. It's okay. What I think we're gonna do up here is. Oh, did I not tell it to pause? Nah, okay, whatever. I had your wood up there, I guess. We can have let's see, building vehicles. Do a limestone mine over here, and then that limestone mine can immediately go into creating cement right here, where this tree cutting area will be going down. So we'll also put some water gathering up here. Right now, I think let's go ahead and put water storage right here. Just because this will allow us to store water for the buildings once we get that up and running, that is. And of course, that will also allow us to have storage solutions for once we need water for farming. Because we will need water for farming, of course. So right now you can see that the farm has enough water in it just because of the rain and such. But sometimes that will, not go great. So we'll see how that shakes out.
And we know something about the gravitational field and the radius of each planet. And so I came up with a ranked list where it's basically the ratio of the escape velocity to the molecular velocity. Sorry. If a planet has a large escape velocity and a small expected molecular speed, I ranked it high on the list. If it has a low escape velocity, like a small planet, not much gravity, fast-moving molecules, I put it low on this. So this is a ranked list, my ranked list of where I would expect to find atmospheres in the solar system. What's going to be first on the list? Jupiter is going to be first. Why?
Super high gravity.
Yeah, so Jupiter has the largest mass. It's also fairly far out in the solar system, so the gases are not particularly hot. So this is large, and that's pretty small. So indeed, Jupiter is first on the list, and right behind it comes Saturn for similar reasons.
And of course,
Neptune.
Uranus and Neptune.
Uranus. Then comes our planet, Earth.
Then Venus, Mars, and lastly, of course, the one that
Pluto.
doesn't. Not a
Or
planet.
Pluto,
Not a planet.
no longer a planet.
Then why are you putting it in the planet list?
Titan, which is a
Is a
satellite
moon
Neptune.
of Neptune, yeah.
Or say a moon of Neptune.
Well, if you're doing that, then you also need to do Titan,
Then
Enceladus,
comes Mars.
and
Then comes Titan, Titan, which is a satellite of Saturn.
Saturn, Enceladus, maybe Europa.
And let me continue the list a little bit longer.
I don't know. There's a lot of fucking places on the solar system that have atmospheres, dude. Okay, so we may have just saw that we can also build rubber
Ganymede.
maker. This will make rubber out of diesel and coal. Okay?
Io, Callisto, Europa, Mercury, and our moon, and then I stopped there. Of course, I could go on and on because there's lots of other smaller moons in our solar system, but I wanted to get at least to Mercury, which is the other planet, and I wanted to get to our own moon in order to make the list interesting for us. So that's the rank list. Now, we know a lot about this because we can detect planetary atmospheres from a distance. We can detect it by going there with an unmanned vehicle. So we know pretty much whether these objects have atmospheres now. And I can draw a line under there. And actually, the line is right where I broke the columns. That's roughly the line. From observations, we think that these planets have atmospheres, and these do not. So our ranking based on that was pretty successful. Maybe not quantitatively, but at least qualitatively, it gave us an idea of where we could find atmospheres in the solar system. Other questions on that? It's a pretty simple argument, and I think pretty powerful to give us that kind of good result. So let me try to make a little sketch of the solar system then, because there's a little more that has to be said about this. Because remember, what I didn't bring into here was the molecular weight of the gases. I use a constant value for capital M as I did these calculations. So if we've got the sun here, then going out in order, you've got Mercury, Venus, Earth, Mars, and then quite a bit larger. I'll draw these with a little bit of size to them. But then quite a bit larger, you have Jupiter, Saturn, a little smaller, Uranus, and Neptune.
Neptune. Heard it here first, folks. It's Neptune
So,
now.
now let's consider this molecular weight effect, the heavy gases versus the lighter gases.
Okay, I appreciate this
For
guy,
Mercury,
but
it turns
is
out
a
that
bit
both would be lost. I'm going to
dry.
put two arrows here. I'm going to label one L and one H. L for the light gases, like hydrogen, and H for the heavy.
Try moving
time,
further. Let's go greenhouse effect and
upstairs, we
habitability.
did this systems experiment where we had a tank of water, and we tried to
It's
analyze
a
it.
system experiment, tank experiment. Okay, let's do that. It's 30 minutes
We're
ish.
We're going to be talking about a simple example of systems analysis. I put the term up here. Almost everything we deal with in science, engineering, even everyday life, has some elements of system analysis to it. The simplest kind of a system, kind of like the one I have here, consists of a reservoir where you store things and inputs and outputs. With that definition, I think you can imagine a wide variety of things that might resemble this. For example, the heat budget of the Earth, which we'll be speaking about next week. You can store heat in the Earth's solid parts in the atmosphere. You can have heat coming from the sun, which is the input. You can have heat radiating to space. And it's the nature of that systems analysis that will help to understand the climate of the Earth. If you look at the hydrologic cycle, for example, let's look at the atmospheric part. How much water vapor do you have stored in the atmosphere? What are the inputs? What are the outputs? Only by understanding that way can we really understand how water vapor is handled in the Earth's atmosphere. Same thing for lakes. A lake has a storage capability. It has inputs. It has outputs. The carbon cycle. There's carbon in the atmosphere stored there, inputs and outputs. In other words, almost everything we deal with in life has some elements of a simple system like the one we're dealing with today. So this is meant to be nothing special about it. It's just an analog for many of the things that we'll be dealing with in this course, and you may run into in other circumstances as well. So we have to first understand those three components, right? The storage, the reservoir itself, the input, and the output. So this is a thin tank made of plexiglass, and the dimensions you will need, the dimensions are here. The inside dimensions of that are 59 centimeters in length, 2 centimeters in width, and 25 centimeters in depth. So if you need to compute the volume of this, you can do it easily from those dimensions. It has a little pipe, a little hole in the end, at this end. You can't see it from where you're sitting. A short little pipe, a valve, and then it flows out into the sink and down into the drain. We'll need to know that that valve is about 6 centimeters below the bottom of the tank. I'll explain why that's important in just a moment. The input is this little rubber hose right here. It's controlled by a faucet, and I can change the rate at which water is flowing in just by twisting that valve. And then the output comes out the valve, and that's a valve, that's a controllable valve, but I'm going to leave it set where it is for right now, and we're going to just leave it and deal with it in the form that it's in. Any questions yet about this simple system I have here? Okay, now the inputs and the outputs, we're going to use capital Q for this. It's the volume flow rate, and it'll have units of milliliters per second, or if you like, a milliliter is a cubic centimeter. It's a centimeter by a centimeter by a centimeter. And the way we're going to measure that, and Patrick has agreed to help me with this, if you can come on up, try that stopwatch, try starting it, stopping it, and then resetting it over here.
So we got that on.
Okay, is that going to work? So I'm going to pull out this pipe. This is a 400 milliliter container. So we're going to time how long it takes to fill that up, and then we will just get the flow rate from that. So I will give you a countdown. 3, 2, 1, start. And as soon as that reaches the top there, you can stop it. Okay. So the flow rate coming out of the valve right now is Q is 400 milliliters divided by 7.41. Can you do that calculation for me? 400 by 7.41. 53.98, and the units on that are going to be milliliters per second. So we're going to be doing this over and over again with different flow configurations, Now, what I've got to, you can sit for a few minutes, it'll take a while now to get this set. I'm going to try to determine the nature of the valve. How easily is the valve letting water out of the tank? That's going to be a critical part of our understanding of this system. And I'm going to tell you that Q out will take the form of some constant times the square root of Z effective, where Z is the depth of the water. I think you would expect that the deeper the water, the more pressure there is trying to push water through the valve, and so the faster Q out will be, the larger Q out will be. So we have to determine the, well, this constant. This constant will depend on how I have that exit valve set. And if I were to change it, I'd have to redo the calculation of K again, but I'm going to leave it like it is. We're going to let this come to a steady state for a minute, and then we'll do a calculation. Now, what is the effective? If the water depth is here, we measure Z as the height from the bottom of the tank up to the water top, and then we add 6 centimeters to it. So Z effective is Z plus 6 centimeters, because that gives us the depth all the way to the valve itself, and that's what's going to be pushing the water out. The point is, even when the tank is empty, if there's a little bit of water in that pipe, that vertical pipe, you're still going to be getting some water running out until all the water in the pipe is gone, and then of course Z effective would be 0, and then of course Q out would be 0. So we're going to determine this. How are we going to do it? We're going to simply solve this for K, so it's going to be Q out divided by the square root of Z effective. Rocks in the stream, but the outflow is going to be controlled by the depth. So last time upstairs we did this systems experiment where we had a tank of water. So that's the goal today, but before I do that, I've got to talk to you about the fundamental laws of radiation. Now, I mentioned this the other day when we were talking about the stratosphere and the thermosphere, but if you have an object like anything in this room or the sun or any object at all, and you plot the emitted radiation as a function of wavelength, I'll use the Greek letter lambda to represent wavelengths. That's the distance from the crest to crest of the wave. It looks something like this. I'm going to draw a bunch of curves for different temperatures. These are called black body curves. It's also referred to sometimes as the Planck function. So if you've got a book on physics, look up black body or look up the Planck function and read what it says about this. Now this would be for a cooler temperature. This would be for some intermediate temperature. And this would be for a high temperature. So for example, this might be the surface of the Earth with the temperature at 288 Kelvin. This might be for the surface of the sun with the temperature of 6,000 degrees Kelvin. And notice two things about this. When you make the temperature greater, of course, you're increasing the amount of radiation that's coming out at every wavelength. Every wavelength, the intensity of the emitted radiation increases with temperature, as does the integral under the curve. The total sum of all the radiation is the area under each of these curves, and that total increases as well. Furthermore, notice that the peak of the curve shifts with temperature. It's there for the cooler temperature, there for the intermediate temperature, and there for the higher temperature. So the color, if you like, the color of the radiation changes as the temperature of the object changes. Now, there are names for these particular aspects of the radiation law. The shift in the peak is referred to as Wien's law, and it's given as by the following formula. Lambda max is equal to a constant.
So something that's really cool about what he's talking about right now is, like, this is how light bulbs work, right? Or at least incandescent light bulbs work. Basically, by passing enough electricity through the tungsten, you were able to straight up, like, get it to glow at such a temperature that it was emitting visible light rather than just infrared light or UV light, depending on, you know, what side of the divide you fell on.
Remind you of the electromagnetic spectrum for a second.
Yeah, the EM spectrum here. And like black body radiation is like the reason that you can feel warmth from someone else. Well, it's the reason that like night vision goggles can work to see people, like thermal vision. I'm not sure if it's exactly why you can feel other people.
The human eye is sensitive to those waves.
Yes, we are. Very sensitive to those wavelengths.
As we spoke about last time, the ultraviolet is over here, and the infrared is over there. Microwave is further over, and then radio waves are further over to the right, and X-rays are here.
And gamma rays and etc.
So just to remind you, you might want to remember 0.4 and 0.7 as the range of the visible part of the spectrum. Now, let's do a calculation here. For the sun, the surface of the sun is approximately 6,000 Kelvin. If I plug into that formula to get lambda max, it's going to be 2897 over 6,000. That's approximately 0.48 microns. I'll write it here as mu-m, micrometers. And that is going to lie
right about there.
Right about there. Roughly in the middle of the visible range of the spectrum.
Any wonder
that's
we
kind
can
of interesting.
Use that
you
as
might
our
want
site.
to think, is that just an accident? I'll say more about that later, but make a little question mark there. Why does it happen? Yeah.
What was the 6,000 again?
The surface temperature of the sun. Is it just an accident? That's my question to you for thought. Is it just an accident that the sun's peak radiation happens to fall in the human range of eye sensitivity? Interesting question.
No,
Let's
it is
do the
not.
same thing for Earth.
It is not an accident. In fact, it is evolution. If, for instance, our sun had a peak in the like above 0.7 or maybe below 0.4, we would probably see in ultraviolet or infrared rather than, quote, visible light spectrum, because that would be what would be available to us, and it would be how we would, it would be like what's most common. And in evolution, always is lazy, and it goes for what's easiest. If your peak of the sun is sitting at 0.45, then it's going to be, or 0.48, it's going to be going after that easy segment right there in the center. But I think I'm going to take a break. I'm not going to say I'm bored by this because I like this type of shit, but I don't think everyone else likes this type of shit. And so, like, I don't know. What I'm going to do instead is I will take a break and we will come back and probably watch some more depositions of InfoWars, because that was kind of fun and I got to yell at them for that. But don't get me wrong, climate change and climate stuff is coming back. I will be going offline briefly, but I will be back shortly. Soon.